Thanks for having me. I'm going to talk to you about how 6G will provide the essential infrastructure to augment the human capabilities. Human capabilities as in enhancing our ability to handle proximity, our ability to handle and create knowledge, and enhancing our productivity overall. So let me start with this view here. This is inspired by the book of Harari on Homo sapiens, who makes the point that our human capabilities have been shaped through human evolution, basically to become a hunter-gatherer. But over a couple of thousand of years, our human environment has changed significantly. We are now living in an urban environment, and the number of people that we deal with has enormously increased. The density has increased from 1 person per square kilometers to 100 per square kilometer, and in urban environment, even thousands of people. We were shaped as a hunter-gatherer to work and live with 150 humans. So still today, this is the amount of people that we can have resonant, effective relations with. But the number of people we interact with has diabolically increased to 100,000 of people. In a city, in a company like Nokia where I work, 100,000 people are an email click away. But these are not the same resonant, effective relationships as the 150 immediate. Also, actually, the whole globe is within reach. You heard about the expression of 6 degrees of separation. I reckon actually in our profession, if you look on LinkedIn, we're only 2 or 3 degrees of separation away from each other. So we need help to handle and have more effective proximity with the people we interact with. Second is about knowledge. And the knowledge at the times of the hunter-gatherer pretty much stayed constant for thousands of years. There and that bay, you can go for fishing, that bear is dangerous, these berries you can eat, and pretty much that stayed constant for thousands of years. But since the Renaissance, the human knowledge has increased more than exponential. The doubling period has actually accelerated enormously. In the Industrial Revolution, it was a few decades that the human knowledge increased. A few years ago, it was within a year, and actually now it's doubling every 12 hours. And I'm really talking about knowledge, not just about collected data, but really learned experience. So we need help to handle that. And the human brain did not evolve in the same way. Actually, what this Ebbinghaus curve says, you will have forgotten most of what I said within a month from now. So we need help. Now, the good thing about this Ebbinghaus curve is I can reuse slides, and you still hopefully find them interesting. Actually, this particular figure on productivity, I have used 2 years ago at the very first 6G summit in Levi in Finland, where I made the point that we will use ICT to enhance the productivity. Productivity as in effectiveness of manufacturing, producing goods, but pretty much everything we do as humans. So it's the goods that then are used in leisure time to play, to learn, and actually to then become more effective and more efficient in the next cycle. Cycles of a week, cycles of a generation. So productivity. Productivity as in outcomes per unit of input, humans, surface, raw material. And a good measure of human productivity is the GDP. And this is a graph from the book of Robert Gordon, Rise and Fall of American Growth. And it shows that in the first half of the previous century, the human productivity growth year over year has increased thanks to inventions of the second industrial revolution like transportation, car, petrochemistry, steel. So it went from 1% to more than 3%. But in the second half of the century, it declined again. The growth declined again to less than a percent. And that despite the invention of the internet, despite the emergence of mobile networks. And so what is the reason? Well, it's because the network was designed for consumers. We use the network to watch video, to do shopping, so not very productive. And so we need to change that. But since my first talk at the 6G Levy Summit, COVID happened. And during COVID, the amount of e-commerce has peaked by several tens of percent. So within 6 months, we have achieved a rise that otherwise would have taken more than 6 years. So we've seen that having an e-commerce infrastructure has been essential to keep our economy going. Now, this was only possible because the investments to roll out that infrastructure happened already more than a decade ago. And so that realization will stay, and we will see an increased and an accelerated investment in ICT. So there's basically two industries that we can distinguish. There are the physical industries, think of the retails, think of transportation, mining, and then the digital industries, think e-commerce and banking. Now, these digital industries are the ones that have the majority of the ICT investments, more than 70%, although they're only 30% of our economy. And they are at a healthy 3% growth year over year. The physical industries, they are the largest part of our economy, more than 70%, but the ICT investments are at 30%, and they are at a less than 1% productivity growth. So the whole idea of Industry 4.0 is to bring ICT technologies to enhance the productivity also in the physical industries. And so with COVID and the experience and the realization of the importance of having automation, remote access, we will see an acceleration of investment. So you see the red curve already. This is what I showed you earlier of the e-commerce infrastructure, but then also the physical industries, the lead physical industries like retail and transportation will accelerate their investment. So you see the inflection point, that purple dot, will happen 3 years earlier than initially planned. So this is based on an analysis that Bell Labs Consulting has done. And also the laggards, think agriculture, for instance. Also there, if that inflection point will happen already this decade. And so we see an inversion of ICT investment now by 2030 in the physical industries by 65% of the total ICT investment, so proportional to the size in the economy. Now, it's also important to realize that these investments will happen this decade, before 2030, before the commercial rollout of 6G. So it is very important to then think, okay, if these are 5G investments, what is the new application, the new use case that we will design 6G for? And in order to understand that better, it's good to have a look at the past and the present. And every new generation, about every decade, has optimized the use case and the application of the previous generation, enabling it to do it at better performance and at lower cost. So 3G has improved the voice services of 2G, and as a new application, provided high-speed internet access. So the new application in 4G was then enabling higher speed video, so downloading YouTube and social media, and also machine type of communication, while at the same time cost optimizing the internet access and also enabling now zero cost voice. In 5G, the new use case is industrial automation, while we improved and also on the video and allow for real-time video conferencing at scale. And now the question is, what will be the defining use case for 6G? It's important to have that new use case because that will drive the direction of the new specifications, influence how we design the future network, and also be an inspiration source for the research in that direction. So, and our thesis is that it will be a massive deployment of sensors, massive deployment of AI, and that will allow us to connect physical worlds and human biological worlds with digital twin models in the digital world. So let me explain that a bit more. But before doing that, in the theme of the proximity, productivity, and knowledge, most of these generations have addressed the augmentation of human proximity. It's actually only with 5G that we really started addressing to improve human productivity. And then with 6G, we will start improving also our capability to handle and create new knowledge. And now you may question, yeah, wasn't the high-speed access to data with 3G already improving knowledge? No, it only improved the proximity to knowledge, the access to knowledge. Whereas now in 6G with AI ML, we will truly have augmentation of our knowledge creation. So here is another way of looking at this. So 5G has improved the connectivity between humans and machines. In 6G, thanks to the massive scale deployment of sensors, we will have a much richer connectivity of the physical world, a richer connectivity of our own biological world, and then twinning that with models in the digital world. In the digital world, where we then apply AI ML to get a better understanding in real time of what is happening in the physical worlds. And that is important because these digital twin models, for instance, allow to transport the model. I can be transported and be with you as if I were there in a holographic experience. These digital twin models allow to understand and anticipate needs, simulate possible outcomes, and then take decisions back in the physical world for more optimal productivity. Same is true for our own biology. These sensing capabilities allow for better healthcare, but it also makes our interaction with the world more intuitive, enhancing the human-machine interface. Let me explain the importance of these digital twin models a bit more in detail. It's actually already happening in 5G. So there are already digital twin models in factories to keep the state of the machine, to anticipate the need for maintenance or repairs. And actually also in a wide area network, we see the concept emerging of digital twins of cities, and even at a precursory state, digital twins of ourselves with recording of Fitbit data and health apps. Now, it's already happening now in 5G, but in 6G it will happen at a much larger scale of sensors and AI deployment. So that will have an important impact on the architecture of the network. So you see here a simplified view of the network with the access part, the anyhole to the edge cloud, and then the IP optical transport to the centralized cloud. And now looking at the deployment of these many sensors, they will create an enormous amount of bandwidth to upload in real time data to the AI ML digital twin models distributed over that infrastructure. And think of these digital twin models as 3D maps with layers of parametric information, but then also more abstract, self-learned models in AI ML where we continuously update the weight factors within the AI model in one location, but also in real time across locations. So this will have an enormous impact on the utilization and the bandwidth requirements of the future infrastructure. Let me now illustrate that a bit more, how we use these digital twins to optimize productivity. So first, in an example of farming. So this is an example of urban farming, vertical farms, where we reuse warehouses to install vertical farms. And so that enhances the productivity because it's close to the people that need to produce the crops. So we reduce the transportation time and the need for refrigeration from 5 days to almost 0. And then you have more fresh produce delivered. We also improve the productivity, the use of water by injecting the water really at the roots of the plants. We also reduce the lifetime, the growth time from 40 days to 12 days by optimizing the light cycles. And then the overall productivity per square meter also improved by almost a factor of 400 because we are using these multiple shelves, optimize the fertilizers. And actually it's a very protected environment. We actually need zero pesticides because there's low risk of contaminants. So in order to understand that use case better, we have built our own small vertical farm in Bell Labs in Murray Hill in New Jersey. So you see here a view of our vertical farm setup. In the upper left, the real world view. In the lower left, you see actually there's a drone flying in between those shelves. And the purpose of that drone flying between those shelves is to inspect the growth. And you see the fisheye view from the drone perspective. And then on the right-hand side, you see actually a simplified digital twin model of that setup. And you see how we remotely control autonomously from a server the flight path of the drone. You see how that drone, thanks to localization techniques, follows a predefined path with depicted with the green lines. Now, the whole purpose of that drone flying there is really then to create a digital twin of the growth itself. And so that you see on those next view. So you see the view, the rare view or raw view of what the drone is seeing. You then see how we inspect by leaf segmentation in the lower left, how we looked at the growth quality by just looking at the colors. And then also you see how we are able by image classification to inspect the growth quality. So that is one example how we create a digital twin model of the physical world in order to optimize productivity in farming. Here is another example. So you see here the view of the conscious factory in Oulu in Finland. This is where we produce our radio systems. And here we apply these concepts of industrial automation using 5G and digital twin to keep the state of the factory. And you see humans in the factory, but they're no longer doing the production. They're no longer doing the manual tasks. That's all taken care of by the robots. The humans are there to supervise and to do the creative product improvements, the production improvements. So we do that thanks to the digital twin models. So you see here how that is our knowledge engine to keep the state of the production of the stock. And then also how we use 5G for remote control of robots, for the navigation of robots. And these automation concepts have helped to enhance the productivity. The lead time has improved by 80%. The overall productivity has improved year over year by 30%. And because we're taking out the human error and allowing for intelligent video inspection, we have reduced the number of defects by more than 50%. So overall, an enormous improvement also of the quality. So these are two examples how we use digital twins as a perfect knowledge engine to have an understanding in real time what's happening in the physical world and use that to optimize and augment our productivity. So in order to make that happen, we can already do that at some level in the 5G era, but in the 6G era, we will do that at a much larger scale, and that will allow us to augment our proximity, so sensing at a distance, sensing capabilities that human senses cannot have at very different frequency ranges, but then also augmenting our presence, our ability to represent ourselves or other things at a distance. Then our ability to augment our knowledge, to handle the knowledge. These digital twins allow us to understand what's happening in the worlds, simulate possible outcomes, anticipate needs, and then also decide on actions to take back into the worlds. Actions that allow to offload humans from the mundane tasks. Think mechanical tasks that machines are better at, but also inspection tasks like scanning thousands of images at a second and recognizing faults or doing image recognition. So offloading humans and leave machines to do what they are best at. But at the same time, also augment humans and let them do what they are best. So that means learning, solving very complex problems, being creative, and taking care of each other. And these are typically then also the things that we mostly enjoy. So to make that future happen, 6G will become the essential infrastructure. And for 6G, for that network infrastructure, we have identified 6 research vectors. So first is the AI/ML native air interface. The second is new technologies for radio, in existing spectrum and in new spectrum. Radio not only for communication, but also using the ubiquitous availability of radio as a sensor, a network as a sensor. And when we start sensing the world, we also need to trust what we communicate over that infrastructure, what we are sensing over that infrastructure. Given the different use cases, we will also have extreme connectivity in an architecture that is pretty much a network of networks, where the endpoints are again a subnetwork with very specialized requirements. And then last but not least, also an important architecture innovations, cloudifying and disaggregating, opening up an enormous set of new possibilities in architecture design. So let me go through them one by one. So here first about the native AI/ML air interface. So what is the problem that we're solving? We want to have a communication between A and B over a channel, and through decades of engineering, we came up with the well-known model of transmitter and receiver with the front end, the modulation, the coding, and then the scheduling of the MAC. And we're using AI/ML already in 5G to basically optimize these different functional blocks. Now, what we're trying to do in 6G is take a clean slate, do away with the complexity of these different functional blocks, and just let the two endpoints in real time figure out how to communicate with each other. And you see how that significantly reduces the complexity of these layers, how that is also a paradigm shift on how we design radio interfaces. And we've done already first experiments in that new space with native AI/ML air interfaces in Bell Labs. You see here how how the AI/ML air interface self-learns the constellation depending on the channel conditions. Then new spectrum technologies. So first of all, new technologies in the existing bands, the low band, the mid band, and the millimeter wave, that will be refurbished for 6G as we can expect. But there will also be new bands. We already talk a lot about using sub-terahertz for 6G. There's a lot of research going on, high capacity and unique sensing capabilities, and I'll get to that in a minute. But there's also a drawback. I mean, as you can see from the lower scale, the reach of those sub-terahertz wavelengths is limited to 100 meters. So it's really confined to indoor spaces. Another important use case or spectrum are the bands just above the current midband, so from 7 to 20 gigahertz, which provides us with bandwidth comparable to millimeter wave, but with a better reach. So say more than 0.5 kilometers, allowing us to do capacity enhancement from existing cell sites in urban environments. And then we can also expect that in the low band there will be additional bands to also address the wide area coverage over multiple kilometers. So as already said, these new spectrum technologies are not only there for radio communication, but we want to look more into using the ubiquitous radio infrastructure as a sensor. Already today, we are able to do localization with wireless technologies. And you see here a proof of concept that we have built in and have tested in Arena 2036. That is an experimental factory in Stuttgart, where we use 5G for the tracking and localization in real time of a robot. And we can do that with 10 centimeter accuracy. Now, going to 6G, with the wider spectrum, with the higher frequency and the narrower beams that we can form, we will have a much higher precision. And it's not only localization, but using it as a radar, it will also give us volumetric information. And there are material-specific back reflections that we will be able to use. Is it a metal surface? Does the body contain water? Is it a mammal or a human? So combine these sensing informations with also AI/ML, and you create a radio network with the sixth sense. So staying with the industrial automation, we will also boost the requirements there, looking at the extreme networking where the end point of a network is again a network. Think machine area network, think a car area network, think a body area network. And within those area networks, you will have very extreme requirements, sometimes life-critical requirements. You don't want the brake of your car to fail, 9 reliability. And the response times need to happen also in a factory within hundreds of microseconds. And synchronicity will be even in the nanosecond range. So network of networks with very specialized requirement in specific subnetworks. And then another important architectural theme is also the disaggregation. We have already the paradigm shift to Cloud RAN that we see in 5G with O-RAN. And we have already first prototypes where we virtualize not only the core, but also the radio access network, and where we do the physical layer processing on common off-the-shelf hardware like a GPU. And we can expect new accelerators, new types of XPU processors emerge in future, and also AI/ML accelerators. And so this allows us in a flexible way, thanks to cloud-native design principles, to instantiate RAN functions like the distribution unit, the centralized unit, or the core unit on a slice-by-slice basis, scale them on a slice-by-slice basis, and optimize their location. So that's already in 5G, but the microservices approach actually allows us to do a lot more. We can now think of dissecting the RAN and the core functions and have a fresh look at the partitioning and the architecture and optimize the location and the functions themselves on a need-by-need basis. And then last but not least, the security. As the number of devices increases, as the number of networks, subnetworks increases, the fact that we have open interfaces and have components from different sources, the fact that functions run on a heterogeneous cloud, private cloud, public cloud, web-scale cloud, and that within those data centers we have software from open source, from multi-vendors, we have different updates, patches, so an enormous surface of potential security attacks. With that goes also the use of AI/ML with its own security risks. So we need to address that in new ways, and we need to design security and trust into a zero-trust infrastructure and design these concepts from the ground up in 6G. So hereby I'm reaching the end of the talk. So it is about all about augmenting the human capabilities, for which the 6G infrastructure will be an essential network. And I talked first about the 6G era application, so connecting the worlds, the physical world and the human worlds with the digital worlds. And then also the 6G technologies, of which we have 6 research vectors. Thank you.